Hello everyone, the title of my presentation is on the algebra of data sketches. Let's start with the classic problem, namely the cardinality estimation problem. The aim is to estimate the number of unique elements in a data stream while having only sublinear storage. The most popular cardinality estimation algorithms are k-minimum value and hyperlog. They are based on data sketches that allow to concisely summarize corresponding fundamental sets. The idea is as follows. We have a data stream that can be treated as a multiset. We are interested in finding the cardinality of corresponding fundamental set. We create a sketch that summarizes the fundamental set. Based on the sketch, we construct an estimator for the cardinality of the fundamental set. The possibility of simulating set theory operations on fundamental sets based only on data sketches has been lately considered in a few papers. The idea is as follows. Assume we have two sets A and B, and for each we create a sketch. Now, based on sketches A and B, we would like to estimate the cardinality of set A, set B, the union of sets A and B, the intersection of sets A and B, and the relative complement of sets A and B. In our paper, we generalize this problem to weighted sets. Namely, we assume that there is a weight associated with each element. A weight is a positive real number. We define the weighted cardinality as the sum of weights of elements of a set. Then we consider the problem of creating sketches that allow us to estimate the weighted cardinality of a set, as well as union, intersection, and relative complement of two or more sets. In the paper, we discuss the following use case. We consider the braid chain architecture. Namely, we assume that there are two sources, A and B, and two paths of nodes that leads to the scene. The paths are connected by the crosslinks. On each link, we have packet loss with some probability p. Here, A1 denotes the set of packets received by node A1. Natural questions that arise while analyzing such network are, for example, what is the total size of packets from source A lost up to the layer I? Or what is the total size of packets from source A that are always present on the upper path? We see that the answer to such questions can be expressed in terms of operations on sets and weighted cardinality. Therefore, if we could simulate set operation based on data sketches saved at nodes, we would be able to answer these questions and also many similar questions. Let us now briefly discuss how we create a sketch. The basic idea is based on the paper by Baquero from 2009. As the input, we take a string S and the size of the sketch denoted by small m. We initialize all positions of sketch, capital M, to infinity. Then, for each element of a string and for each position of a sketch, we take three steps. First, we calculate a hash value, which we assume is uniformly distributed random variable. Second, we transform this random variable to obtain a random variable from the exponential distribution with parameter lambda I, where lambda I is a weight of the element. Third, we save the minimum of the currently saved value mk and computed value e. By the properties of the exponential distribution, mk is also exponentially distributed random variable, but with parameter capital lambda, where capital lambda is the sum of weights of all elements. Finally, since the expected value of mk is 1 over capital lambda, we can construct an estimator for the sum of weights as the harmonic mean of reciprocals of sketch elements. Such estimator is unbiased and is also well concentrated. Let us now assume that we have two sketches A and B created for two datasets A and B. Then we can create a sketch representing a union of sets A and B as a pointwise minimum of sketches A and B. This construction is easy to justify as we get the same sketch as we would get by observing elements belonging to the union of sets. This is the case since the minimum of set A and minimum of set B is equal to the minimum of the union of sets A and B. This reasoning can be generalized to any number of sketches A, B, C, and so on. And the estimator of the weighted cardinality of the union is very similar to the original sum estimator. To estimate the weighted cardinality of the intersection, let us note that it is equal to the product of the weighted union and the weighted Jaccard similarity. Weighted Jaccard similarity is defined as the weighted cardinality of the intersection of sets divided by the weighted cardinality of their union. We prove that the weighted Jaccard similarity of two sets is equal to the probability that sketches A and B are equal at position K for each position K. These allow us to define unbiased estimator of weighted Jaccard similarity as the number of positions in which two sketches have the same value, divided by the length of a sketch M. The reasoning can be generalized to the larger number of sketches. At first, we need to generalize weighted Jaccard similarity to be the ratio of weighted cardinalities for intersection and union of any number of sets. Then we define generalized estimator in similar way as the basic one, by counting the positions on which all sketches have the same value. We define an estimator for the intersection based on the estimators for the union and the weighted Jaccard similarity that we have defined earlier. We show that this estimator is unbiased, and we find the formula for the variance of this estimator. We also show that this estimator can be generalized to any number of sketches based on the previously defined generalized estimators for the union and weighted Jaccard similarity. As we compute a union of sketches, we obtain a complete sketch that can be used for next operations. However, it's hard to obtain a complete sketch representing the intersection of sets. Therefore, we define a partial sketch representing the intersection of sets. Namely, if two sketches A and B have the same value on position K, we copy this position to the intersection sketch. If they differ on position K, then the position in the intersection sketch is set to 0 and treated as undefined. To estimate the weighted cardinality for the union based on such partial sketch, we use the same estimator as for complete sketch, but we simply consider M prime defined non-zero positions of the partial sketch. To estimate weighted Jaccard similarity, we just divide the number of defined positions N prime on which AK is equal to BK by the length of the sketch M. To estimate weighted cardinality of the intersection, we take the product of estimates for the union and Jaccard similarity. All these estimators are shown to be unbiased. Moreover, the idea can be generalized to the larger number of sketches. Finally, let me remark that analogical results holds also for the relative complement. Thanks for listening.